Okay, welcome everybody. Today is November 16th in Dallas time, and we are in the regular weekly Robot Builders Night virtual. We're going to do the usual thing, go around the table and share what we've got to share, new projects, old projects. Well, we have a special deal tonight with Paul presenting on diagnostics library that he's got for Ross. Quick housekeeping. So we have only one thing, I think, on the horizon in December, and it's looking like it could be a double header. I think Jack Jones is still on track to tell about his robot journey and a multi-year from early in school to college. And Paul, are you still on track for the December one? Or
if you want me, yeah.
That would be great. And can we put a title down before we forget? Roughly? Or what topic?
Self-driving trucks.
Self-driving trucks. Cool. Big ones. So that'll be cool. And aside from that, I guess I switched away too soon. I have one other thing to put up, and I'll put a link for this in the chat. But there's been a lot of talk lately that we've had in this session on the RPi 2040. I haven't been following it, but I didn't realize there's bigger versions and smaller versions of it. So here's somebody that's made a robot with the smallest version of the 2040 and a couple of motors and a light battery. And how's that for a robot? 70 milliamp hour battery, a couple of 3-volt motors driven straight off the GPIO pin, and some balls for rollers. And how is this going to work? See, this is the amp display, of course. Why do they have to do that to us? The video will resume in 5 seconds. Oh, come on. There we go. On the mobile phone, it viewed a little differently. Oh. Well, this is bad. This viewed totally differently on the mobile phone. So Tom's Hardware, here we go. And the guy's talking, a minute 57.
Standard in single board computers. And now
let's just jump ahead.
It's got to also use a generation has video at up to
Okay, this is not what I expected. This is failing miserably. Let's go. How can this be? Let's stick one more moment. Crossing fingers? No. This is terrible. Okay. Anyhow, I'll have to find a better link and put it out there because this is just not right. But it's anyhow kind of cool. It shows it pushing a battery around a little AA cell. I thought that was kind of fun, kind of cool. So I'll get a better link somehow and post it in there. But that's all I've got for the night.
Has anybody here actually built any robots that small?
Not quite that small.
Not this big. There's a fellow out in Seattle. We were out there one time at their Robothon. Reached into his pocket and pulled out a robot about this big and laid out a bunch of M&Ms on the table. And it would drive over the M&Ms and determine what color they were and sort them by color.
Wow.
Yeah. He had a little stack in it. It would drive forward and pick one out, and then depending on the color, it would push them in different directions. So there is some value.
The smallest I've ever built is basically, this is 2 PyCon 0 motor controllers and a 0 underneath there, a 0W. And the chassis for it ended up being bigger because of the battery, of course, but it was using N20 motors. So the whole thing was about this big, but I could have made it smaller if I'd used smaller batteries. So I think it's totally possible, especially, like that's not very big at all.
Well, it's really the hardware is the problem. It's not the software. We've got these parts that are that big, come with 20 volumes of manuals.
Well, note that that's 4 motor controllers, actually. It's not, if I took off the second of these boards, it actually would only be the PyCon 0 and a Pi 0W. And so that's only this big then. And so, yeah, the possibilities of making a really tiny robot, but I just found it irritating. It's too, you know,
And David, you were talking about going to the Robothon out there in San Francisco. And the year I went out there, they had the micro sumos, and the mini sumos are like 100 centimeters square, and these were 10 centimeters square. So you're talking, these, fit on your finger kind of things. And there weren't very many of them. There was a couple of teams from Taiwan that had some, but they had little micro motors in them. And, it was just amazing what they were doing with this just itty bitty bug looking thing.
Well, it is kind of cool to think you could reach in your pocket and pull out a functioning robot, put it down on the table.
Mm.
Yeah, the same guy has another one here. He's touting that this one is powerful enough to pull a USB cable. Isn't that something? Here we go. Check that out. Boom. Pull that cable. Okay.
A lot of force.
Okay. Well, that's all I had. Just some silliness. So let me stop being silly and pass the table over. Ray, you've got some videos and cool stuff to share.
I think it's cool. Hopefully, you guys will. Okay, I'm gonna back this up. Yeah, that covers the controls there. Anyway, I don't know. I think I actually said something incorrect here. This is the controller for a riding mower. This is the ESP32 baseboard. It has LoRa, and this is RC controlled, but this servo actually controls the transaxle. If this is pulled up, that's, it goes faster and faster forward, and push down faster and faster in reverse. This wire leads off to a linear actuator that does the steering, and it's driven by a just a single channel DC brush motor controller. And then I had to have two separate DC to DC converters, one for the ESP32 and another for this servo to get the 30 kilograms centimeters out of it. You had to drive it at 6.8 volts, so not the normal 5 volts. Anyway, I think I explained some of that, but
this is basically the control unit for the mower. This is an ESP32 with LoRa and a display. This is the failsafe when I hit the red button over here. It's supposed to turn off the engine. The engine is off right now, and the little green light will light. So that'll basically cut out the circuit. This is a DC to DC, well, not DC to DC, a motor driver, and these are two power supplies. Switch mode power supplies takes 12 volt. One brings it down to the 6.8 volts for this servo, and then the 5 volts for the board. So I can show that. So the servo, like if I push it forward, it pulls that lever up, and that's forward motion. If I go backwards, it's backwards, and that actuates the lever on the transmission. And then left and right is there.
it's actually backwards, right and left.
There's right. Doesn't quite go back to neutral, but I have to shift where the thing is because it didn't quite
got it on. And the clutch pedal has to be pulled back all the way. And I went in and got a bungee and put it on and pulled it back.
Ray, that's hydraulic drive.
Yeah, it's a hydraulic transaxle.
So have
Is
you
that-
ever actually cut grass with this thing?
I'm sorry, I can't hear you.
Said, have you ever cut grass with it?
Oh, yeah. Yeah, the throttle's pretty sensitive, pretty touchy.
Ray, you told us a few months ago that you'd driven up to Oklahoma or somewhere and come up with a transaxle. Is that this actual one we're looking at?
Yeah, I got it from Staten Inc. He had the best price at the time. I get a lot of this stuff from Surplus Center, but he had a good price. He makes motorized bicycles. And,
What's a good price, if I may be so bold?
I think this one was like 260 something. I think he's still got them on his website. I can look. Surplus Center had them, but they were more expensive. So.
And does that require a separate hydraulic motors, or is the transaxle itself the motors?
Yeah, no, it's driven by the gas engine on the mower.
No, I just mean that separate to drive the wheels. Is there a separate motor, or it's just
Oh,
like?
no, it's self-contained. It's got
Cool.
a, let's see, what is it? I think it's a variable displacement pump and a fixed displacement hydraulic motor.
Very cool.
Anyway, careful.
When you putting it on the big loader?
So I don't wreck anything. Anyway, that's the transaxle sticking out of the back here. So that's what I had shown. So I had was a little nervous about it because, you know, the thing goes off and at speed, you know, and I didn't turn the blades on or the deck on at you know, during that, but could have. It, you know, it's just a mechanical, you know, belt driven deck. But I was a little nervous because you know, if I can't stop it, it could do a lot of damage. So, you know.
A new category, the Rainbow Star.
The Rainbow Star, what's that?
David Anderson is holding up Rainbow Stars. That's beyond Gold Star, I think.
I'm going to stick it here on Ray's forehead. Ray, you'll have to sit still.
Oh, okay.
Ray, that is nicely done. That's really cool.
Yep.
And
So I need to, I've got different tires for the back. I still want to try a setup where I have two brakes on either side of the transaxle. And then that way I can do, you know, basically pivoting on one wheel. Whereas that's, you know, pretty much an Ackerman setup, which not as easy to program, you know, as far as, you know, the kinds of motion that we're used to dealing with. And yeah, you know, it's a lot of back and forth, and you know, you can't spin around on one wheel, you know. But it was that transaxle was about half the cost of setup that you'd need for zero turn. You have to buy essentially two of those, and they're, you know, they're both belt driven, but they're independent of each other. So
That time, a
Anyway.
couple of weeks ago, you put a marker on the back end and drew those patterns in your garage floor under
Yeah.
where life would normally park. And in that case, were you braking the inside wheel to get those sharp turns? Those were very sharp turns.
Well, that was differential drive
Okay.
on that platform, so I could spin on a wheel, and you think the way that you mow, it's with a riding mower anyway, because you can't make one wheel turns. It's you mow differently, so
You have to
typically
mow like a
like,
you have to mow like a Zamboni.
basically, yeah, you gotta cover all the ground. But
I may have mentioned this before, but when I was young, on my grandfather's farm, his old International tractor, there are two brake pedals, and they're right next to each other. You could hit them both at once, but you could also hit one or the other. So when you get to the end of a row, you just hit that inside wheel, and you're perfectly lined up for the next row. It was really easy to do.
oh, okay, yep.
And on those, the throttle, is you just set it. It's a lever.
Yeah, it's fixed. Yeah, you kind of want it. So same thing with the riding mower. You just set it at one position and vary the speed. However,
Those old long stroke.
Yeah.
A single cylinder tractor.
Sounded like it.
Anyway.
All right. So Ray, I'm gonna take a quick bounce back because you showed a really big one, and I found the video of the one I was trying to show. So we're gonna go from Ray's riding mower to this little guy right here. How's that for a robot?
Wow.
A Raspberry Pi. There you go.
Pretty small.
Yeah.
Definitely sort your M&Ms with that one.
Well, if you had a sensor.
That sounds like something that's vaguely obscene. Sort your M&Ms with that one.
There you go. Got your M&M sorter right here. Okay.
On the related note, SparkFun has put out a line of boards they call Small, spelled SMO with, I think, an umlaut and L or something like that. And they're little stackable boards that use, I think, ribbon cable. I'll have to look, but they're really, really tiny boards. I think they're 10 mil by 30 mil, and I think it's an ESP32. I'll take a look, but they're designed as small, and you can stack them, and I think it's ribbon cables between, so you wouldn't be stuck with a cutie pie. You could probably use one of those, and you'd end up, well, although actually in our personal robotics group, the playing around that Adam Green. Anyway, the guy that's in our group who's doing all the experiments with I2C slaves and stuff on the RP 2040, and who read the entire spec cover to cover, he's had quite a lot of fun with the RP 2040, particularly the PIO part of it, and using one of those. And I don't think there's really any limit on what you can do with an RP 2040. It's kind of an amazing little chip. That PIO, he's actually currently playing around with, and he's going to probably implement the encoders using the PIO. So you would just have hardware support for the encoders on the board. So yeah, it's very, very cool little board. And because you can buy the chips, you could make your own board even smaller than the Cutie Pie. You could go even go nano.
Just get rid of all the I/O and it's tiny. Yeah.
Yeah.
Cool.
Ball grid array, maybe.
All right, so let's go. We've got I think Dave Ackley, you had a question. Let's go through that, and then after that we'll throw Paul Bocher to the floor, and let's get the correct pronunciation. Did I butcher your name totally, or what's the correct pronunciation, Paul?
Bouchier.
Bouchier. Okay, I butchered it. Bouchier. Okay. Just slap me up if I...
It's French for butcher, so yeah, that's kind of appropriate.
Okay.
You may remember that we one time some years ago had one of our robothons out at Chez Bouchier.
Yes, indeed. That was fun.
Okay, cool. All right, so moving on. So Mr. Dave Ackley, you've got, let's carry on. You're looking for an answer, I believe.
Yes, I am. Had we decided whether we wanted fixed focus or autofocus?
Oh, this is the Oak Delight question, Kickstarter.
That's right.
Well, the real question is, what are the pros and cons of each? I mean, obviously, autofocus is if you need to focus on close things and far things and a mix between. And if you're just looking out a long ways, then the fixed focus would be nice. But, you know, why? My big question is, what use case would you not want autofocus for?
Well, the way they described it was that if you have your camera on a mobile platform that's moving around a bit, the fixed focus will have a great deal of time actually focusing. And so for a fixed camera, the autofocus is great, but from a robot that's moving around, I think the consensus seems to be that the fixed focus is actually the preferred one.
Yeah.
Makes sense.
Is
Now, the other-
Kareem here this evening?
I don't see him.
See him. I think he's had experience with both, and Ted and I wouldn't speak for him, but I do think he concluded that the fixed focus was easier to work with for whatever reason. I know, you know, if you're going to be doing a lot of image processing stuff, focus can really screw that up.
Yeah, and you don't want it focusing on the wrong thing. That would be a problem if the autofocus decides not to focus on what you're trying to get. So
Well,
I can see fixed focus would work.
Does anybody remember what the close in limit of the fixed focus was?
12 inches,
Yeah, 30.
30
You
centimeters.
know, that seems, it's any closer than that, you're running into the thing anyway, you know?
Yeah.
Yeah.
Well, the other thing is too, I don't know what the depth of field is on the camera, but also, sometimes when you're doing vision work, you actually put a blur on the image. So
Pretty blurred.
yeah, what I'm trying to say, it's only the center camera we're talking about. The depth cameras are all fixed focus already. So I think that, like if, let's say you're at 10 inches, is it really going to be so out of focus that it can't recognize the object that you're trying to hunt for, whatever it is? If it's a cone, at 10 inches, it's going to be blurry, but it'll be okay, and like David said, you'll be your camera's not right sitting on the front bumper. It's back probably 6 inches on your robot, and maybe even 10. It might even be 10 inches back. So it's probably not a big deal. I went with fixed focus on mine.
I feel horribly neglected. I haven't been asked yet.
Well, sounds like the fixed focus sounds like the right answer. I appreciate it. Thank you.
Murray, what do you think?
About what? I got a whole lot of opinions.
Well, the topic was the Oak fixed focus versus autofocus, specifically for the Kickstarter that a bunch of us are doing.
Well, if you're actually asking me, David, I think I've made up my mind. It is the fixed focus is the best one.
Okay.
I think we have a consensus.
It does sound that way. And I was just trying to go back through the old notes because we had, I can't remember which meeting it was in. And I don't know, maybe Doug, if you could help me, if there's an easy way to search the chat records we have. But we've had this discussion before when Kareem was online, and we talked about the fixed focus versus autofocus question in global. So there's a whole like 20-minute discussion on this topic in our archive somewhere.
My memory is, inaccurate as it is, my memory is that Kareem had worked with both and that he had preferred the fixed focus.
For the lack of anything meaningful to say, I need to ask about this fixed focus versus not. With fixed focus, how are you going to get the PID in there? That's what I want to know.
Oh, it'll
never
still
mind.
go.
The behavior trees will handle that, Harold.
Oh, okay, got it.
You're just trying to Wind us up, Harold. With
Stirring
that
the pot,
super
baby.
cool.
Stirring it up from the bottom up, baby.
We're gonna get you in queue after Paul with this visor that you have going on, because that's rocking it there. So, okay. So while we were going, I think I've nailed it back to. I've traced it back to this. We had this discussion in the September 28th Watch Builder Night Virtual. So round about 9:17, if you look at the time tag in the lower left corner of the recording, around 9:17. I asked that same question, Dave, and we had I think there was a nice long discussion afterwards with weighing in on actually some of the reasons why, some of the factors to consider about that. So depending on how deep you want to go down that rabbit hole, it was on the 28th of September.
Okay,
Let me
thank
just
you very much.
ask a question, Dave. The cameras that we have used in this group, like the CMU cam and the Pixie cam and so forth, those are all fixed focused, right? Is that right? Doug is nodding his head.
So yeah.
I haven't had any problem with that.
Yeah. I thought in general it was supposed to be a lot more robust. I thought the autofocus mechanism was somewhat delicate, maybe, and you didn't want to jounce it around. I thought that's what the reasoning was. Is that?
There's some autofocuses that do the equivalent to what a speaker is. They're just a voltage variation, and they do, with the vibration, they'll sometimes go nuts and won't focus. We used to have problems with them on the remotely piloted airplanes and stuff like that.
Huh.
So vibration.
The vibrations would knock them out.
Yeah, and what Andy just said is the same reason that OpenCV gave for going to the fixed lens. They mentioned the acoustic autofocus, and they also mentioned that Apple had recently had a problem with theirs. And anyway, I'm just saying I think for us it's pretty clear you want to go with fixed focus.
Is there any possibility of putting a secondary lens on it or something, where you can put a manual motorized controlled focus on it or something if you wanted to?
Probably
not. And the reason why I say that is I believe there's a glass plate in front of it. I mean, I could be wrong, but
as answering my question, I think we probably beat it to death. So I appreciate the inputs. Thank you.
Sounds good. Or you could just get one of each. We could see what happens. So.
Okay,
Andy,
if you want to buy the other one for me.
Andy, if you really wanted to, you could take it out of the metal case.
I don't know what it is we're talking about, so
okay.
The Oak D Light.
Oak-D-Light. If you go to Kickstarter, look up OpenCV.
Okay.
We'll put a link in the chat here in a moment.
I'm on my phone right now, so.
That's okay. It'll be in the chat records, which you can find. I just put a link in the chat for, and we post these on the DPRG website. So if you go to dprg.org news, and then in there you can find links to these recordings in the chats that we have. So, yep.
Andy, you must have a great phone.
Why?
Your picture and the audio is great.
Oh, well, it's sitting right in front of me. So it is a 4K spatial AI powerhouse. Tiny.
Yes.
Gotcha. Okay.
And a whole bunch of us got sucked into it, where there's a whole lot of investors you're looking at right now. We've all put tons of money into this thing.
There's a lot of stuff happening right now on the digital front, from digitizing things from cameras and stuff like that. So yeah. I just picked up one of the high dollar 3D scanners, and what's interesting is right after I picked that up, there's a lot of stuff coming out that brings it up a lot cheaper. So
Yeah, it's the nature of technology. You invest in something, and then like a week later, the better one comes out.
yes, there's one that I got a laser pointer at one point in time that has a has a filter that you put on it that puts a grid of dots out in front of you. And I thought that'd be kind of interesting just to put on a pointer and then fix a camera to it, and then you can just, once you take your reference of all your dots, you can figure out what's going on in front of you.
I think that's how the Mars rover does it. They call that structured light. They project a known pattern, and because you know what the pattern would be on a flat wall, you can deduce the 3D from the distortions.
Yeah. There's one that they've got a picture on here where they're projecting out. I don't know if it's real or not, but they've got a picture projecting a bunch of squares out, but they don't look like they look like they're all parallel, which makes me think that they're done afterwards.
That's what this is.
That brings up an idea. I at one point was thinking about building a house, and at that point in my life, I bought one of those really, really expensive red laser things that sits on an expensive German tripod and spins out a red. Yeah. Has anybody figured out there's something we could use that for in a robotics idea? Because I've still got it downstairs in this expensive German case, and I could take it out and plug it in, or actually it runs on batteries, and get that nice red line everywhere. But is there something I could use that for, maybe?
Isn't that what a LiDAR does?
That is a LiDAR, yeah. When Carnegie Mellon did the H1s and stuff, they were back in the first robot races. They had them mounted up on. They had a kind of equivalent of them mounted up on top of the vehicles, trying to grab scans of the roads in front of them and stuff.
Well, no, this is only providing a horizontal line for building like a house. Like you would project this against a foundation, and you could see this red line that's perfectly flat.
Okay.
Nothing. There's no spinning lasers or anything. It's just there's a spinning laser, but there's no sensors.
Just your generic laser level sort of thing. I got some of
Yes.
that lying around too.
Yeah. Mine's a very expensive German one that I spent a lot of money on. That's down in the box.
Okay, not
And I
so
wonder if I
generic,
could use
but
that for robots.
I've got one too, and it's generic as it gets. So
Acculine Pro.
So
Yeah,
in that case, the sensor is your eyes, right?
Yeah. I was just thinking I could maybe, using the Pi camera or something like that, just go and look for the red line, maybe.
Well, Ray's done a lot of experiments where, if you see an object, it's going to distort the line that's going to go up. So you can, by seeing things that are different from just the line, you can tell whether an object's there, whether it's closer than you or further than you. He's done those experiments. Yeah, I think he's actually running in one of our contests, but I don't know how they.
Yeah, they make it's like a Fresnel element that basically makes a series of dots that look like a line, and you can get them. They're very cheap. I got all that stuff from AIXIZ.com. And you can get different power levels, for he sells just about every color laser there is, and they're pretty reasonable. The line lenses you can get, I think, up to almost 90 degrees, so you can shine it for a fairly wide angle, and it's bright enough that you can easily see it. So, and you can even get like a bandpass lens if it's infrared, and so you're making just a little bit easier for the camera to see the line, because it's that bandpass lens is only letting in the wavelength of the laser, so it looks pretty bright. Everything else looks, it's suppressed, it's dark.
So Ray, I'm on the AZIX or AZIG or whatever I don't know how you pronounce that site.
Yeah.
Is there something I should look for, like this dot laser? What's it called?
They're just I think he just has it under lenses or.
Okay. I can get a cosmetic laser. I can combine that with the ear thing.
Yeah. You could go to town.
Well, man, there's too much on this site. I give up.
Yeah, I thought it was. You might be able to just do a search on line lens. I don't know how good his searching is, but.
Quick find.
Okay.
Cool.
Shall we move on then? Is that good?
Sure.
All right. So I'm thinking, Paul, are you ready to go?
Yeah, absolutely.
All right.
Um,
So without further ado, Ross
So-
Diagnostic.
Sure. So I think one of the motivations for this kind of tutorial talk is that one of the differences between hobby robots and professional robots is the existence of diagnostics. Because if you're building something that's going to be deployed and serviced by people, you have to have something for the operator to know if the robot is faulty or not, and then something to guide the field engineer to what is faulty in it. And I actually used this ROS diagnostic architecture in a defense robot. It was like a mini PackBot kind of style robot, and it worked great. And it is so easy to use. I thought that, the advantage of I think diagnostics bring advantages to the hobbyist as well if it's easy enough to do. And so what I hope to show you by means of this demonstration project that I package that I put together is that it is extraordinarily easy to use the ROS diagnostics and so I want to show that. And so what I did was, and what I'm going to present is the architecture of the ROS diagnostic system and how you use it. And so I built this demo to illustrate that. And what it does is it simulates typical robot hardware devices, sensors, and such, a GPS, a camera, and a battery monitor that all emit diagnostic status. Because if you think about it, your robot has software modules that are driving hardware, that are looking after hardware like GPSs and batteries and such, and they have interesting data available to them, like the battery charge level and the number of satellites in view and the estimated GPS accuracy and so forth. And if you could just get at that in an easy to use way, it would and be and is very helpful. So in this project, each of those 3 hardware simulators is a class with a method that's called at 100 hertz and given a sinusoidally varying value that has a period of about 10 seconds. And so this simulates the loop that you would typically have in a robot where different sensors are sampled at some period between maybe 25 hertz and 100 hertz. And the reason for feeding these modules a varying value is just to induce behavior, to give them some live data to act on so we can see the diagnostics working. And so each of the GPS camera and battery monitor classes, they don't actually monitor a camera or a GPS or a battery, but they're really a platform, the simplest platform that I could figure out to emit diagnostic data that would be relevant if it were a real hardware controller. And I've got the link here. And let me ask you, is this slide showing okay?
Yeah.
Looks good.
Okay.
Yeah.
So this is the architecture, and I've color-coded the blocks. I'm going to talk through them first, and then spend a couple minutes looking at the code that implements them, because it's very, very simple. But the green blocks are functions provided by the diagnostic architecture, so you don't have to mess with them. And the yellow blocks are functions that you would have to write your own anyway, because if you've got a GPS piece of hardware, you got to write a GPS piece of software, and similarly with battery and camera. So the way this demonstration works is you've got a sine wave generator that provides varying data for the demo, and at 100 hertz it calls each of these simulator classes and provides it with the next value of the sine wave. And the sine wave, as I said, has about a 10 hertz period. So, after 1/100th of a second, it's going to increment the sine wave by 1,000th of a period. And so I'm going to talk first about the way publishing diagnostic data works. And the way that works is you have a class, and the class instantiates an instance of a diagnostic updater and passes it the period at which it should publish diagnostics onto the /diagnostics topic. And then as the simulator gets called and runs its loop at 100 hertz, at the end of each iteration of the loop, it calls the diagnostic updater saying, okay, you can run now. And most of the time, the diagnostic updater just hands back control and doesn't do anything. But when it gets time, every second or whatever you configure it for it to emit diagnostic data, it calls back into the status reporter callback. That's a method that you provided and that you registered with the diagnostic updater when you instantiated it. The status reporter callback, that is your code, passes back an array of diagnostic data. And this is a list, an array of key value pairs. So a key can be, and they're both text strings, so they can be anything you like, from battery charge level, and the value would be perhaps 20%, and to perhaps number of satellites, and the value might vary between 1 and whatever, 0 and whatever. So your status reporter callback passes back an array of these key value pairs, which the diagnostic updater then publishes onto the diagnostics topic. So all of your hardware, all of your software modules that are looking after hardware do that, and they all publish diagnostic data from the piece of hardware that they're looking at onto the /diagnostics topic. ROS does provide a Runtime Monitor graphic tool. It sort of gives a basic view of what's coming across the diagnostics topic. But what you really want to do is instantiate this optional block here, which is the analyzer subsystem. And ROS provides a generic analyzer that's very powerful, and that you can configure with a YAML file. So just a plain old text file that tells the analyzer what analyzers you want to use to analyze the incoming diagnostic streams, what keywords to look for in diagnostic reports, and how to present them. And then the analyzer subsystem forwards this processed diagnostic data onto a diagnostics ag, for diagnostics aggregated topic, which you can view, which can provide a very user-friendly presentation just with the built-in RQT robot monitor. Or you can put your optional alerting app to monitor the /diagnostics ag topic. And that was what I did on this little backpackable robot. Was I built something that went here that digested a list of diagnostic data that it should watch for, and threw up alerts onto the operator console. So Are there any questions on like the architecture and the concept of how this thing operates? Because if not, I'll show just a very few number of lines of code that it takes to emit the diagnostic data first, and then I'll look at the config and we'll look at the thing running. No? Okay.
Sounds good. Code review.
Code review. So I'm going to. So this project, I put the GitHub URL of it, the Diag demo, and in the include file are 3 files: the GPS simulator, camera simulator, and bat simulator.h. So I'm going to look at the GPS simulator, and so we instantiate. So the in the class definition, we just declare the class, and then there's one public method, simulate GPS, which gets sign val. So this is the external method that gets called by that exciter object, if you will, the class that calls in with a sine wave value, and then we have some private methods, some private data here, and this is the key one, this diagnostic updater, which I call GPS updater for this particular update. There's also a frequency status, because you oftentimes care about, so you get some extra stuff beyond what I've described in terms of like knowing how many satellites your GPS receiver can see. You also care whether the GPS receiver is publishing GPS data at an appropriate frequency. If it's publishing too slow or too fast, you got a problem. You also care whether the updater is even putting data on the diagnostics topic, but I'll get to that in a little bit. So anyway, but this updater is the main thing. That corresponds to the diag updater here in this drawing. So it's a thing that's going to get instantiated inside the simulator and that will do the callback. Okay, so we're inside the GPS simulator here. We've got some low private data for like min and max GPS rates, and class data for how many packets it sent, how many it dropped. In the constructor of the class, here's the key line here, the GPS updater, we instantiate it, and we have instantiate a GPS frequency status object and pass it in a minimum rate, etc. And we configure the GPS updater object with its hardware ID, which turns up in the diagnostics data. So think of this as a label for the diagnostics data that this updater emits. And then here's the key point where we register the callback. We add to the updater in this object the get GPS diag status method, and that's where it calls out back into our class to get the current GPS status, and then we add the frequency status task. So then at 100 hertz, the simulate GPS method gets called, and it goes down, and it has a little time delay, and it decides, every 20 hertz it drops a packet. Otherwise, it increments the number of packets sent, and it tells the frequency monitor that, hey, I got called. So that keeps everything timely. And it computes the number of satellites based on the input sign value. So that's some static data. So this is really simulating what your hardware driver would be, the kind of data that your hardware driver would be tracking. And then right at the very end, we call the GPS updater with we call its update method. And this is where we give control to the GPS updater object, and it can then call back into the callback we registered with it if it's time for it to send an update. Otherwise, it just returns right away and doesn't do anything. So this is how the callback thing works. You know, we loop around through this at 100 hertz or however often your control loop is cycling, and at the end of each time we call the updater, and if it's time for it to send a diagnostic packet onto the diagnostics topic, it does so. Otherwise, it just returns. Now here's the method that we really care about. This is the callback, where the updater calls back into us and passes in a reference to a diagnostic status wrapper that we are then going to populate with data from our class. So if the number of satellites, which you recall we computed based on our input sign data, is greater than 4, then it populates a summary saying its status is okay. If it's less than 4, then it populates a summary saying that the status is in error and they're insufficient status for the RTK picks. And then it populates some additional data, the number of packets sent and the number of packets dropped. So I'm going to demonstrate that now. And there are a number of launch files in this project. The one I'm using, the most usual one is the diagdemo.launch. And away we go. And it fires up the RQT robot monitor and launches the node that runs the simulators. And now I'm going to also...
Paul, you must be using the Cadillac of GPS units. You can actually have something that does 100 hertz update.
You know, this is only a demo project.
Oh, okay.
So
especially RTK, I thought those were,
Yeah, I know. That's
like
more like 5 hertz.
Or something, yeah, very low.
Yeah. So I'm going to run the runtime monitor, and if you recall, that's the thing that looks at the raw /diagnostics packet. It's not super helpful, but it's some basic data, and we can expand this and look at the warnings and errors as they occur, and it's just printing the diagnostic data that's coming across the diagnostics topic. We can also echo ROS topic echo /diagnostics, and we'll let that run for a little bit. And what you're seeing here is some reports from the camera updater saying the camera status is okay, and here are the number of packets received, number of packets dropped. And if I Control C that and scroll back a little bit, we can find a report from the GPS updater with the GPS status saying status was okay, and then here's the frequency status, and that's running okay too. The actual frequency is this, and if we go back far enough, we'll find a battery report that the charge was okay, and the battery charge value was 56.0077%. So this is by way of showing that this is the work that the diagnostic updater does for you, for that little bit of code that we looked at that hands back a couple of key value pairs in a message back to the diagnostic updater. When the callback is called, it generates this message with timestamps and all the overall status and the messages and the values.
Paul, I didn't see any of the timestamps in your display. Are those part of the monitor?
Good catch, David. This runtime monitor doesn't show very much. It's it's not all that useful. The timestamps really only appear on the topic. However, things get a lot more useful when you turn on the analyzer subsystem and you encode some generic analyzers, and then your data starts to look pretty interesting. So all devices, we can expand each of these, and you'll see you got like an overall status that has changed from red to yellow to green. Everything's gone green now because, you know, the 10-second cycle has resulted in all the devices being happy. But pretty soon we start to get unhappy on GPS. The diagnostic status has insufficient satellites for the RTK fix. And you've got warned devices here. You've got error messages that are shown. And you can also, there's actually a print a console print in the battery simulator when there's a ROS warn statement in the simulate when the battery is being simulated. If the charge goes below 10%, it prints out a ROS warn charge message. And one of the really nice things in ROS is Swiri Console is a much better version of ROS Console, and much better because it prints out messages that are sent to the console sorted by the node that sent them. So in a typical ROS robot, you've got lots of nodes or processes, if you will, and they will all list down, as many as have emitted console data will be listed down here. And so you can see the ROS warn and ROS error and ROS debug messages from each node. I've only got one node that's printing here, so we only see one node. But what I want to show that is producing this rather nice hierarchical view of a battery, a camera, a GPS, and their statuses is all of this is being filtered out by on the basis of one file, diagdemo.yaml, which declares the analyzers. So it declares a GPS group of data that should be analyzed, and it's to be analyzed by the generic analyzer, which is a part of the diagnostic system. It's to be placed in a path under a GPS heading. There's a timeout. Remember I said you want to know if your device, if your driver stops emitting, like maybe your driver dies and stops emitting diagnostic messages. So it'll time out after 5 seconds. And the filter for diagnostic messages is it contains GPS updater. And so that's what results in this nice little GPS updater here, appearing like here and here in the warn device and here in the error device.
Paul,
That's
excuse
about
me.
all you have to do.
This YAML file. Oh, that's me. Sorry. This YAML file is the input to what?
The YAML file is the input to the analyzer subsystem. So this is the analyzer YAML file here. You know, there's like a dozen lines in it that declare a generic analyzer for 3 of the subsystems, and then I actually declare a custom analyzer. And because I want to, there are times when you want to look across devices. So I imagine that the GPS maybe could have a battery in it, and maybe you want to alert if the battery in the GPS goes low, but only if the GPS is seeing less than 4 satellites. It's a made-up scenario, but you get the idea of spanning, of analyzing across hardware devices and across different message groups. So I declared a GPS battery analyzer, and there's source code for it that I'm not going to go into because it's like little deeper than I really plan to go in here. But it's a plugin to the analyzer, and it gets plugged in based on this YAML file, and produces this GPS battery analyzer status here. So that was the YAML file that tells the analyzer subsystem which analyzers to instantiate and gives the generic analyzer filter conditions to tell it that enable it to select only the diagnostics from the subsystem that you want to display under the proper heading. And then that all gets displayed on the RQT robot monitor, and your optional alerting app that might put up alerts on a console, on an operator console, can also subscribe to this diagnostics ag topic and do whatever you need it to do. So that's all the demo that I had, but I hope it's been helpful in terms of let's see, GPS battery analyzer.h, GPS battery analyzer.h. That's not what I wanted. I wanted GPS simulator.h. In terms of how easy it is to declare a callback and get the callback called so that you can emit whatever key value pairs you decide are interesting onto the diagnostics topic, and then how easy it is to get those displayed.
Paul, I have a question.
Go.
Can we go back to your diagram? I'm trying to understand the operation here as you described it. So basically, we have this 100 hertz sine generator that's dummying up our data for us, and it's driving the GPS, battery, and camera drivers, whatever you call those.
Yep.
And in the case of the GPS, you had a counter that said, well, count down to 20. So we're really only going to be running at 5 hertz. And at that point, it itself invokes the callback?
No, it calls the diagnostic updater every time it loops. So at 100 hertz, it calls the diagnostic updater with the update method. And that provides the diagnostic updater a way to get control if it wants to. And the reason it would want to is because a second is up and it's time for it to publish diagnostics. So at that point, only after a second has elapsed would the diagnostic updater then call back into your program and call the callback that you'd registered with it, which returns the diagnostic data, and then the diag updater puts that in a message on the diagnostics topic. Did that answer your question?
I think so. And those are color-coded in green to indicate that that's part of the system that is given to you.
Correct.
Paul, this is pretty cool. I think I'm learning more every time someone presents on ROS, and this has been the first time I think it's started to sink in with me at the kind of coding level. But I have a question. Am I interpreting the ROS way of things that with this messaging bus, so that, like, by the structure of the YAML, it looks like that one's specifically set up for this analyzer subsystem. But is the idea that in this inliner subsystem, seems to have a kind of a dashboard that gives a hierarchy of diagnostics, red light, green light, yellow light things.
Correct.
Could you just as easily have another style of dashboard that reads the same values but presents them in graph form?
Um, uh,
Uh-oh, bad
it's
question.
not really set up. I guess the short answer is you could build whatever you want into your optional app that consumes diagnostics ag messages. And what I didn't do, and I'll do now, is to show the data that goes across diagnostics ag, because that's actually pretty interesting. You'll see how it's okay. So we'll let that. We'll just exit that now, and so I'll scroll back up to the top of this message. So this is a big long message. All of these dashes are subsections with a message, but the 3 dashes here are the beginning of the message on the diagnostics ag topic. This is what's being emitted by the analyzer subsystem. So it declares an array of statuses, and the first status is at level 0. Its name is battery. The message is okay. There's no hardware ID. Here's the value. The bat updater key has value battery charge okay. And then here's the battery charge status. And here's the battery charge. So this is this group of data here was aggregated from what the battery the updater in the battery simulator produced. Now we go down to the camera, and scrolling on down a little bit. So the camera reports some values, some overall values, and then gets down into the number of packets received and dropped, and the frequency status. You know, whether the how long the window is that it's measuring, how many events there are in the window, and so forth. And then we get down to, at the end of the battery set of data, we get down to the GPS, which again has the same thing in it. So what you're seeing here is this analyzer system has aggregated all of the diagnostics emitted in the multiple messages from the diagnostic updaters and presented them as a aggregate on this diagnostics ag topic, which the RQT robot monitor then consumes for its little display, and you could consume in your app to, you know, plot or whatever you would want to do. All you'd have to do is to receive this message, and then you know, it's a known message type, so you just fish out the appropriate fields and go to town with plotting.
And I presume there are modules for plotting and different widgets for viewing and rendering different things, right? Or is that another topic entirely?
Yeah, that goes beyond beyond my knowledge. Really,
Okay.
the way that everyone does it, you really probably wouldn't do that. What you'd really probably do is, if there are some topics that you're interested in, which there typically are for a GPS simulator, you'd probably be interested in latitude, longitude, number of satellites, and so you'd probably maybe emit them on a topic, on a separate topic, so that you could just feed them straight into RQT plot, or RQT plot is the standard plotting. So the analyzer system is sort of at a higher level. It's sort of at the diagnostic level of, you want to see at a glance whether your system is healthy, and if not, which subsystem is not healthy. it's not really necessarily optimized for telling what the latitude and longitude being emitted by your GPS simulator, by your GPS hardware is.
Okay. It just strikes me that because I think I get that better now because and I'm not used to I haven't thought about a system like this that could handle really complicated multi-layered subsystem in a long time. It just strikes me that when you get to this dashboard level, you really have to know what the metrics are, what's good, what's bad, what's marginal, to be able to define the thresholds so you can simplify it like this, right?
That's exactly right. And when you're building a robot, you would know what thresholds and what diagnostic data was appropriate for these different kinds of devices. And you can imagine motors in here and arm controllers and all kinds of things. And so, yes, you choose the data that you're going to publish, and then up in your optional alerting app, and you might also put in thresholds. I actually put in a gratuitous dynamic reconfigure capability here, where you can configure the low battery threshold. I wasn't going to go there because it seemed beyond the scope of this intended scope of this tutorial. But you can do things. But yes, you can put thresholds down in your hardware monitor because you likely know them there. And then up in your alerting app, you likely know what sorts of things are going to be problematic, like overcurrent on your motors, that sort of thing.
This reminds me a little bit, since Chris isn't here to give me hell about it. I don't know if anyone remembers, but like I'm writing my own ROS, and that's the joke about Chris is he thinks I'm actually trying to emulate ROS. But I guess it's almost 2 years ago, added a module onto my logger that could generate. I'm not sure if it was CSV or JSON, but it basically was, I've got a logger that I wrote on top of the Python logger, and I modified it to generate, I think, CSV. And then it would, at the end of a robot run, push or that data up to a Grafana server. I don't know how many of you are familiar with Grafana, but you can basically configure it so it can receive data. And so I could graph the output of whatever I was sending. And so this is kind of, obviously a lot more advanced than what I did, but basically the idea is to have data generated by the robot either live or at the end of a run. And the reason I'm piping up at this point, Paul, is that one of the things I found was that on a Raspberry Pi, if you do too much live while the robot's running, you actually start to impact on the performance of the robot. So I'm using a message bus, but if I was to overload the message bus with lots and lots of diagnostic data, rather than simply writing it to a log, I would probably be spending or send so much data into the message bus that it would actually affect the robot itself. So have you noticed any kind of a performance hit on this when you're running it?
Well, so you bring up an absolutely valid point that you do need to be judicious in choosing how much data you're going to emit, because you can swamp any processor if you emit more data than it can handle. I do want to correct I made a misstatement before, and I want to correct it. I said that you would probably write your own parser, but I was looking through this, and they've enhanced this to where there's a diagnostic analysis package that didn't used to exist when I originally did this, that can convert diagnostics logs to CSV files for examination and after the fact analysis. So one method of doing this could be to, and a common way of doing this would be to capture a bag file that has some set of topics in it, including the diagnostic ag topic, and then run the play back the bag file, which is a recorded list of messages, into this analysis package and get CSV files out of them to do exactly what you're suggesting.
Yeah. Because I mean, David does the same thing. He takes log outputs and then graphs like his PID controller and stuff like that. We've
Right,
seen that.
right,
And that's
right,
kind of where I got the idea from, was from David, is that basically,
right.
if you don't know what your robot's doing, you don't know what your robot's doing. And but of course, the act of measuring something often alters the thing, and that's been my thing, is that trying to measure things live, I had too much of a performance hit, and so I just dump it to a log and look at it afterwards.
Yeah, and nothing wrong with that.
Mm.
So anyway, this tutorial was really for people who are using ROS, because this architecture is not well documented. I mean, the APIs are well documented, and there is an example, but it's not very clear. But the architecture as a whole is not well documented at all. And so I hope that someone coming along down the road a ways might find this useful.
Well, even for those who aren't using ROS like myself, I found it useful, and there's lots of ideas in there.
Yeah, it really is a pretty neat architecture.
Here.
Yeah, nicely done, Paul. Thank you very much for straight off of a holiday and jumping right in with something like this. That's fantastic.
Well, sure. It's been sitting around for a while, and and I figured I should share it, because there's a lot more interest in ROS than there used to be back many years ago, and so hopefully it's useful to somebody.
More of us dabbling with it, so who knows where it will go, and see. Cool. Okay, so at this point, we didn't have anyone else lined up, except that earlier I saw somebody with some spacey glasses on, and I'm wondering, beyond Harold, might there be someone who has anything who would like to share? David Henderson has something good, then Harold and David and Murray. Okay, that's good. That'll carry us for a while, I guess. So Harold, what is going on with this? You ready for the rave? He's getting set up here. Okay.
Hey, Paul, how many man years of experience do you think you have with ROS? Sounds like you've been working on it forever.
Well, so
Decades?
I started out in probably 2010.
Okay.
So a while, but
decade.
Yeah, now you mention it, a decade.
Yeah.
But yeah, but it has taken off way more than I mean it is like the only viable what's considered like the only off-the-shelf system for this kind of robot.
Do you feel it's getting commercial acceptance, though? I mean, is it?
Yeah, absolutely, it is.
Okay.
And whenever I do my talk, I'll talk about commercial applications, and but it's absolutely going commercial. For a long time it was just researchy, and then the percentage of attendees at ROSCons used to be like 70% academic and 30% industry, but these days that has reversed, because and really the reason is that it comes with so much that you don't have to reinvent, like the logging, the graphing, the diagnostics, the stuff that Chris was showing for, that just makes it possible to build robotic systems and have a decent support structure that otherwise you end up shortchanged on, and that costs you in the long run.
If I remember correctly, you're talking about industrial and commercial applications. Roombas run on ROS. if I remember correctly. And also
Do they?
all those robots running around the Amazon mega facilities, that's all running on ROS too. Now that's probably highly customized for both of those things, right? But the base is ROS. At least that's what I've been led to understand.
Oh, I did not know that.
And aren't a lot of the robot competitions, aren't they largely on ROS as well, like FTC, or no?
I don't know about the first stuff. I don't know. I don't think the first stuff do that because they've got a controller and a few other things, and they got a lot of Java working off and most of that stuff that I've seen.
It's a
Well, I
think
thought,
ROS
I
does
thought
Java.
ROS was largely implemented in Java.
Well, no, I thought it was C++ and Python.
Yes, it is C++ and Python.
Oh.
Mm-hmm.
I have a very brief thing.
Murray, we had I think we had Harold first, and then we had.
is Harold starting? I thought we started waiting for him to get
David
ready.
and then Murray. Yeah.
So what you're looking at, I put the link to the tutorial in the Adafruit Learn section. These are the eyes. The eye lights is what they call them. This was supposed to come out for Halloween. I signed up for an ADA box. So once a quarter, I spent $60. They hit me for $60 and they send me something cool once a quarter. These showed up about a week, I don't know, last week, which is about a week and a half after Thanksgiving or so. But then, so we put them together, and this was they sent me the kit. They showed me the frames and the LED matrix that's on the front of these things and the LED driver that's on the side. I've got it hooked up to Bluetooth so that you're seeing a little bit of the characters go across there. But I can do a bunch of things with it. Like, for instance, I go into the controller. I go into the control pad, not the control pad, the color picker, and I can pick colors as a thing go across. This controller here does a whole bunch more things. I'm picking colors, but I could be picking instead of that because I've already got implemented this Bluetooth thing. For instance, the Quanterion, which is actually kind of where ROS does its controllers things, and you can't hardly see it, but it's got a 3-axis accelerometer on it. It's got a microphone on there and the LED driver. So depending on what you have loaded on this thing, I can make it do like a spectrum analyzer for the EQ stuff. As I'm talking, it does things. And there's 116 LEDs on here that are RGB. There's some in a circle, and most of them are in a matrix. So you do all kinds of fun stuff with them. And that came in a box, and we put that all together. And if you go into that link I sent in there, it has you can't get the AdaBox 20 anymore, but all the pieces and parts that I have, they are available one at a time. On the
Harold, what does that look like from your side?
I'll show you. You'd think it'd be crazy, right? It's extremely boring because all of the stuff is blasting out. And there's I don't know how well you can see that, but you see the slits in there, and that's exactly what I'm seeing. I don't see any of the things that could be coming across.
So no Dramamine required then before you put those things on, huh?
No, not at all.
It's like, oh my God, I'm gonna be sick.
So that means that if we could hack into your glasses, we could take over what you're presenting and make you say
absolutely. The Bluetooth is wide open. You just have to be able to connect to it before I'm connected to it, and it's wide open. So
can it subscribe to ROS data buses?
It probably could. I mean, it's Bluetooth. It's what I'm actually doing right now. What's actually going on here is this. This is on my Android phone. It's just a big old app for sending crap over Bluetooth. And what's on the driver here is an app that receives stuff. And when it has a UART mode. So in the UART mode, I'm just sending things at it, a little bit of text, and putting send. It sends it down. It says it picks it up. Now that's my new message. So I start scrolling it. Now that mode could be to do all kinds of stuff, read the glasses. In fact, one of the examples is called tap mode. And as you look up, the glasses get lighter in intensity. As you look down, they get more intensity. So by looking up and down, left and right, and using an accelerometer, I could probably figure out how to drive my robot by with my glasses on and how I'm looking up and down and tilting my head left and right and all that sort of thing. It's pretty cool. And for $60, did I get my money's worth out of this ADA box? I think the answer to this, yes. I think
you got a big smile.
What I'm going to do with this, I don't know, other than show up to people like, well, I will tell you exactly what I'm going to do with it tomorrow. I did the DPRG list. I sent out a promo code to Code Launch, which I will be at from 5:30 to 7:30 tomorrow. If anybody wants to be local and show up, be my guest. I was on the hackathon team Sunday and Monday, and we did a website for the person, and we did a couple of other things for their app that's collecting health data and that sort of thing. And there's six competitors that all go through like a Shark Tank kind of thing, get on stage, show their video, answer hard questions, and then the audience gets to vote for them, and the winner gets a whole bunch of money, and the winning dev team gets about $1,000 to take home to spread around. So I've been told that I need to put Fix on my glasses, have their t-shirt on, and if we stand backstage, because if they win, they want me to come out to accept with my glasses doing the Fix thing or doing something funky with it. So, it's already got me, some notoriety. So I think it's well worth the $60.
Very cool.
Lots of fun stuff, man. Lots of fun stuff. Yeah, that's about all I got to show off. I will tell you, I'm repurposing my donkey car. I'm going to do a very much Ross 2 thing and get some stuff working on that while I'm waiting to find my big 1/8 as inexpensive as possible 1/8 roller chassis that I can obliterate, so I can obliterate the cone outdoor challenge next time. If I run over the cone, even better. I can obliterate the cone. I know I'll get docked points, but me rolling over the cone, it's a kind of thing. And but it occurred to me that my donkey car that I crashed and just have kind of put together not working. It has a Raspberry Pi. It has an ESC in it. It has a way to. It's got at least one steering servo on it. It's got a camera to put on it. It's got all the things. It's just not big enough to roll through a cow pasture without getting stuck. And I'm like, okay, we're going to start working through that and step by step go through the Ross thing, make sure I can drive it and do all the things I'm with on it. And then I'm going to use that as well as an example to upscale my Zemo, my rover.
Harold, you are so wrong. You will not be penalized. We are so easy. If you just show up with a robot and you can turn it on, you're golden.
Oh, I know. That's what I did in the last one, and my rover didn't come in last place, so I'll take it.
Yeah.
So the most common question that's asked is, why won't it run? and that's what the diagnostics are intended to answer. It's like, why won't it run? That is the most common question.
Paul, the classic answer is, well, it worked at home.
Yeah, you're right.
So what was it that the $60 bought you or whatever?
Okay, the $60 got me the front plate here. You can see this. I got some black frames. These are just black frames. It got me the black frames and battery and some JST connectors. The most expensive part of this thing that it got me was this face plate that's right here that holds all the RGB LEDs on it, 116 of them. A controller, which is right here in the middle. It's kind of hard to see at the moment. I don't have all my lights turned on. The controller that controls them all. It has I think it's some sort of SAMD. No, it's a Cortex board here. If you see that, with a LED driver on it, 3 degrees of freedom accelerometer, a bit of a microphone on it, and it's got some battery connections and a USB-C connection. It even has an
RF.
on-off switch, which is a rarity for these little boards, that sort of thing. And I believe if you were to buy these, I was looking at you. If you look through the link, it puts it out on the whole thing about how much one of these. I think this front faceplate here is like $25, and this driver board's another probably $15 or $20 or something. I don't know what it was exactly. And then everything else got it. It probably came in with shipping and everything just over $60. But I think I got my money's worth. You guys can go look at that list as much as well as I can on all that.
Thank you.
And there was nothing to actually sorter or put together other than slide in the thing. I did learn a bit about a little bit. It's a UF2 thing. So double click on the board here with the bootloader, puts it into drive mode. And so if you want to run they had Circuit Python. I know, much to Murray's chagrin, on the thing. They have Circuit Python, which is what I've got running on it right now. I just drag and drop the stuff into the USB drive that looks like it reboots. It's up and going, and now I can load all kinds of Python stuff at it. You can also kick this into the Arduino mode. So if you want to do your standard Arduino sketches, you can do that too.
Harold, can we help stack the ballot box tomorrow virtually, or would we have to be in person?
I have no idea. I have no idea.
Well, our thoughts are with you at the very least. And if there was some link of how we could do it virtually, you might find some help out here.
Yeah. Okay. I will ask somebody if they can vote virtually.
All right.
And how that works. At the very least, sign up for go to that Eventbrite and get signed up for it. So they might send out a mailer or send out a link to everybody that's there, and you vote on the link. Because I will guarantee you, people aren't walking by and pushing a button or dropping a piece of paper in something.
Yeah. Okay. Yeah. Well, if you could point us at the right thing, then that'd be. Let's see what we can find out.
Okay. Let's see if I can go do that.
All right.
Yep.
I think we had next in queue, we had David Anderson, and then we had Murray, and then whoever else wants to go after that. Thank you, Harold. That's really well done. That's flashy lights. Always good. Not one LED, but 128.
Yeah. Hey, blinky LEDs, man. They always win, right?
You always win. And David, you are muted, I guess.
How's that?
No echo. Sounds good.
Okay. I have just two quick things I wanted to show. One that I just thought of. So I'm going to share my entire screen. That's what we decided you have to do, right? Share the entire screen.
Easiest way to go.
All right. And you guys seeing a waveform? Or a bunch of waveforms?
Yep.
Okay. The only reason I brought this up, Paul, was because you'll notice over there on the right that that's all in green. And that means that all of these different seismic signals are coming in and they're appropriate. And their latency, if you look at the far right side of the screen, is on the order of less than 10 seconds. If the latency goes up to 5 minutes, those all are the ones that are latent turn yellow. And if we lose the signals, they turn red. We had originally had a simpler version of this, but because this is a government contract, they wanted green and yellow and red. So I was kind of tickled by that when I saw your display. They only want to know, is it good or not?
Nice.
How do you like it? Yes or no? Then the other thing, this was from last week. If you guys remember, I was sort of wringing my hands about what I thought was a little tiny bit of overshoot. Murray gave me trouble about it. And Ted suggested maybe that my diagnostics were in error, or I was interpreting them incorrectly, which is a good thought. So I went back, hang on here.
The links, by the way, the links and to the Eventbrite and the promo code are now in the chat. So you guys knock yourself out.
And that's in the evening too. It's not during the day. Okay. Thanks.
Not now. What happened? How do I make this go away?
There.
Okay. So let's see. Let me back up a little bit. Let me show the one I showed from last week that, or basically what it boils down to is I tried to replicate the problem. I actually have a little tweak that would allow it to be adjusted. And so I went in to do that little tweak and I could not replicate the problem. This was as close as I came. The robot's driving in a straight line for, I think, 10 feet, rotates 180 degrees or whatever the angle is and goes back to the beginning. And you can see here, if I zoom in on this, what I was thinking was an over rotation, that it was rotating too far. That's the way I had analyzed it. But I actually went back and I couldn't produce it, the over rotation. And so that made me curious. And so I went back to look at the original one. And what I saw was that, if y'all remember, what I was doing was I was looking at the response of the robot to a stepped function and to a very, very sharp deceleration. I was looking to prove that the output of the PID controller actually goes negative in a real hard deceleration. And so this was the starting edge. And just to recap, this green line up here is the velocity input. The blue line at the bottom is the steering, the rotation input. The squares are the output of the PID controllers, where the solid square is the right and the open square is the left. And the circles are the actual velocity of the wheels, where again, the solid is the right and the open is the left. So here we have this step function where the velocity went from 0 to looks like 850, well, I'm sorry, that 85%. And you can see that the PID controller pulled the velocity up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So about half a second. And when I watched the thing, it just appeared to accelerate. I mean, I didn't see any acceleration curve. I hit go and it just, bam, it just went. Then at the other end, I'm using a real short deceleration curve. You see the green line coming down there. Basically, I was giving it 15 inches to braking distance. And you can see that the squares, the output of the PID controller, actually do drop below and begin pulling the velocities down. And they do, in point of fact, go through 0 and go negative. And so if we zoom in on that, and this is what got me thinking, if you zoom in on that and look at it, you can see that not only do the two squares go negative, but that the velocities themselves for 1, 2, 3, for 4, 5, what is that, 200 milliseconds, so 1/5 of a second, the wheels themselves actually reversed. And that turned out to be the key. And so, not to make a long story any longer, or maybe to make a long story really long, you can see here when it came out of the rotation, you can see the navigation attempting to correct, because as I thought, it was over rotating. But that's not what happens at all. It's not over rotating. It is, in point of fact, and I went back and I looked at a couple of things I can show you. After Ted suggested that maybe I wasn't appropriately logging and reading the logs. So I went back and I did, I've got some, basically some geometrical shapes that are built into the robot that I can run at any time, and just went back to look, and I don't see any evidence of over rotation when I look at the, or under rotation, when I look at the corners. So here we're driving along a straight line, and then we stop here and we turn, actually it's coming this way. So stop here and turn, what is 135 degrees. And I don't see any evidence of all that the over rotation was going on. So let me jump to the, basically what I determined was that I don't have a video, unfortunately. But let's see, can you guys see my hands? I can't see what you see. Can you see this hand?
We can. And we
Okay.
can pin your hand to the display. So we should
Okay.
the hand or the graph.
The hand for the moment.
Okay.
Basically, so when I said go with that square edge, the robot just took off. As I say, I didn't see it accelerate. And when it came to a stop, it did something similar. It kind of went like that. It stopped real quickly. But that's not exactly what it did. What it actually did was it rotated slightly. When those wheels turned backwards and they slid, it didn't slide in a straight line. And that's why the navigation was having to correct. So I was not over rotating. I interpreted that data wrong. What was happening, because that was a peculiar kind of test, and I was slamming the brakes on real hard, the robot was sliding sideways as it came to a stop. So here's one where I just ran it at normal speed. Let me go back and get the big plot.
Robot drifting.
Yes, exactly. So here's the one that we were just looking at. And you can see here now that let me scale this up a little. The acceleration is now a linear ramp rather than just that stepped function. And you can see that it doesn't, the deceleration, I'm giving it 26 or 24 inches braking distance here, and it doesn't have to pull 0. There's kind of an interesting thing going on here. You can see the solid blue are the right wheel. And so it's trying to pull the right wheel down to 0. And it does. But the voltage doesn't actually go to 0 because the robot won't actually move when you're under about 10% voltage. So the algorithm is happy that the wheels have stopped. And it doesn't itself go to 0. It doesn't need to. The wheels have gone to 0. So, and I just thought that was interesting a little bit. And if you look at the other end of this, where the rotation continues, both of the wheels come to stop before they begin accelerating again. And so that, one more. This is the plot for it, and these are in tenth inches. And so if we zoom in on it to see if there are any irregularities, and there's off by 1/10 of an inch, and there we're off by, anyway, I can zoom in on this forever. It never does anything but give a straight line. So that I didn't end up doing any tweaks or anything. All I had to do was just back it down into its normal range of operation, where I wasn't trying to drive it with square waves and drive it with the normal slew rates that I have, and all those problems went away. So it wasn't over rotating, it was sliding. And in that sense, the navigation behavior was doing exactly what it was supposed to do. That is, the wheels didn't know they had slid, but the gyroscope did. And so it corrected for that. And that's all I have to say about that.
I think that you should go up to Canada and try a hockey rink.
You know, we tried to run our robots on the ice one time. It's pretty entertaining. You should try it. The balancing robot will not balance.
Will not work. You know. Hey, so you bring so this raises the issue of slip detection. So what is there a way? How have you looked at, or has anyone looked at ways to detect wheels sliding with respect to the ground? So I see David, and I mean, aside from going in after the fact and looking at graphs and comparing things.
What I have done, and it seems to work pretty well. I've got this working on all the robots because I'm doing odometry from the wheels, but I'm also taking the heading from the gyroscope. If you, let me see how to describe this. If you integrate the wheel, get this correct. If you integrate the angle that's returned by the odometry, you can get a heading, but it drifts over time because odometry drifts over time. Further, if you pick the robot up and rotate it, the wheels don't know that, but the gyroscope does. So even though the two of them, if you integrate them, will produce locations that drift apart. for any instantaneous reading, they should be about the same. That is, the wheels and the gyroscope, the rotation from the wheels and the rotation from the gyroscope should be about the same. And if they're not, the wheels are slipping. Because the wheels will, there's two possibilities. One is that you're rotating and the gyroscope says, yes, we are, and the wheels say, no, we're not. So the wheels are slipping. The other option is the wheels say we're rotating and the gyroscope says, no, you're not. So again, the wheels are slipping or you've been shoved sideways. So in the nominal case, sample by sample, which in this robot is at 25 Hertz. So every 40 milliseconds, the rotation derived from the wheels and the rotation derived from the gyroscope should be about the same, And if they're way off, the robot is slipping.
So to kind of follow through on Carl's question, if we were to try, let's say I'm coming at this now, I've got odometry on my robot and I literally just plugged one of these little IMUs on there. Now, how do I integrate the IMU gyroscope data with the odometry data? Like, is that trivial or it sounds like quite complicated?
No, it's trivial, but it's a good question. If you're running just standard odometry, then every time around the loop, you difference the left wheel from the right wheel and divide that by the wheelbase. That tells you the angle that you rotated through for that sample. All right. Now you do the same thing with the IMU. You're going to have to differentiate it. So you save the last sample of the IMU and you subtract the current sample from the last sample. So again, you have how much did we rotate just during this 40 milliseconds. And as I said, those two should be more or less the same. So you actually need to have some error range in there that says, I'll accept that as the same if they're close to the same, but if they're way off, which they will be if it's sliding, they'll be way off. And they'll be way off for a long time. That's one of the reasons that you have to give it a little bit of wiggle room, because just in the normal running around, there's going to be a little difference. If the wheel hits a bump or something like that. But if they're actually sliding, it'll be a big difference, and it'll go on from a computer point of view. It'll go on for a long time.
Oh, okay. Thanks. Because it's funny that I've probably played around with over a dozen IMUs like over a year ago, just experimenting. And it was actually just yesterday that I put some of that IMU code back into my robot. So I've now got the ability to have a gyroscope for the first time. So
every move is carefully planned.
Yes.
And the trucks, the self-driving trucks also detected slip because we'd drive them on ice, in snowy conditions sometimes. And they had, it was pretty much the same as a little different, but the same concept as what David described. They had a nav box on them though, and the nav box spit out longitude, latitude, or easting and northing, and you check them against the odometry. And if the two were in disagreement by more than a certain amount for more than a length of time, then it would throw an error and stop.
So, okay, so I guess it seems like there's a fundamental assumption that any wheels you have, they're going to slip differently. Because if they slip by the same amount, then the gyroscope's not going to know, right?
But Carl, I thought the same thing, but my experience in running lots and lots of tests, that the errors that you have to look out for have to do with errors in rotation. So what you're talking about would be an error in distance traveled, right? So
because
if you're starting at a certain location, you want to go 100 feet, and both wheels slip the same amount. Maybe you arrive an inch or two short. But that's not that big a deal. But if the difference between the two wheels switch that much, then your angle will be so far off, you'll probably land 10 or 20 feet in error. So the error it's really the heading error, and not, I hear people talk about wheel slippage in the terms of odometry a lot, and nobody really defines what they mean. It's just this vague boogaboo. Oh, wheel slippage,
Yeah.
But in point of fact, my experience is that the slippage in distance traveled is you can ignore. It's the slippage in rotation that screws it up.
That's application dependent though, because going back to the trucks, in an icy parking lot trying to back a trailer up against the dock, and their wheels will absolutely slip because there's a little bit of a lip before that they've got to climb over, and they get stuck on the lip, and so they're not moving, and the nav box says we're not moving, but the wheels say we are moving, and so I'm just saying that your point is good for certain types of robots and certain applications, but in other applications, you really do care about longitudinal slip.
I wonder if there's a way that the accelerometers could be brought to bear on that problem.
Well, the nav box uses, it does fusion of GPS and IMU and gyros. So, the whole thing is all mixed together, and you get an answer out the back end of where the nav box believes the robot is, and you can tell from that how far it actually traveled and how far the odometry says the wheels believe they traveled.
So in that case,
that's all under the hood.
When you say actually travel, that's saying that you give more credence to the nav box.
Yes, because wheels are known to slip.
And nav boxes don't have any error?
These were expensive nav boxes. These are like $50,000 nav boxes with satellite-based augmentation and laser gyros and you name it.
But if you simplify it, though, I mean, I'm thinking in the back of my mind as we're having this discussion about our little hobby robots or big mil-spec trucks, I'm thinking about, well, what about cars with independent ABS on each wheel, or conversely, cars like the Teslas where you can push the thing to the floor and it won't skid the tires, any one of them, which is like the inverse ABS. So how I just wonder, how do those systems do it? And is there any lesson there that could be applied to what we do here?
Well, I'm going to save my next $50,000. But now let's be honest. We're buying off-the-shelf things today like IMUs for 10 or 12 bucks that were that kind of money 10 or 12 years ago.
Yeah.
Yeah, I was just explaining to somebody about this whole idea of a size of rice time of flight detector that can use 20 milliamps and give me up to 4 meters of range with a centimeter accuracy for less than $20. I mean, come on. We live in a different world now. And I was just going to report very briefly that I just got word from Adam Green, who's the programmer from Seattle, who's working on our RP2040 motor controller. And he's played with PIO, and I can report that his PIO experiment, what did he say? That he's managed to get the quadrature encoder signal up to 2.84 megahertz, which seems like plenty. So the PIO on the RP2040 can handle rocket ship robots, I think. I think we're like 10K or something like that. Is like, David, what would be a normal encoder frequency? Like way below 2.84 megahertz.
Well, it depends on how many ticks you have,
Yeah. Well, let's say 3,000 ticks, that's what?
The ones I have on the little robot I've been running around in here, I ran it up as high as I could just because I could. Those are 500 count encoders, optical encoders on the motor. So that's 500 counts per RPM, per revolution. And I actually trigger on rising and falling edges going both ways. So I have 2,000 ticks per revolution. And that gives me at full speed at 25 hertz, something like 5,000 ticks at full speed. And that's, you could get by with an order of magnitude less than that for sure.
And this is 2.84 megahertz, so I think we're fine.
Well, more is always better, although Kareem said his students had run into trouble because they were getting so many encoder ticks and they didn't have high enough resolution numbers they were storing them in, so they'd get fold over and so forth.
Well, what Adam was doing was he had set up a function generator and tried to whack the RP2040 as hard as he could, and he could get all the way up to 2.84 megahertz before it started missing ticks. So, yeah,
I think you'll be okay.
I think I'll be okay. Yeah.
Cool. Hey, Murray, was that your update or?
That was my only update. I had the message just came on like while we were talking, and he gave me the update, and it's pretty impressive. So I have to say that I don't know this guy at all. I think he's from the Seattle Robotics Group, but he did read the RP2040 spec cover to cover, like in detail. Like he's really amazing programmer. And so he's already tested this thing out. And yeah, I couldn't possibly pay this guy what he's worth, you know?
Well, cool. I'm sorry we made you wait so long for a short weekly update, but that's worth its weight. That's quadrature encoders at 2.5 megahertz. Now I have to think, what can we build that'll? Okay.
Well, suppose you had 18 motors.
Then you'd have to multiplex.
I'm just saying you might need that kind of rate if you had some complicated articulated thing.
Yeah, well, this motor controller is going to be for 2 motors, so we'd have to split the 2.84 megahertz in half. Has somebody got like a motor going on in the background? Harold, are you making noise?
No, my mic is muted.
Oh.
I
I can hear like sounds like someone like
I mean,
looking eggs.
I'm good at making noise and all. But
There you
this
go.
time it ain't
Whoever it
me.
was just turned it off.
Rain stick time. Okay.
Rain stick.
All righty.
David is
I
in
need to go to the bathroom now.
So what else is going on this week? There's a
Sound of running water.
What's that?
Now we're down in hobo mode. Okay.
Yeah. Well, I'll get my banjo out in a minute.
Okay. Very nice.
I had a question.
Pat, what's up?
Been programming, playing around in Platform IO with VS Code and Platform IO and GitHub. So I've got a couple repos on GitHub and get everything going. So I'm programming on my laptop, save it up. I basically push it into GitHub. Then I pulled it down into the Raspberry Pi. But when I go to look at my code for my Arduino code, none of my libraries get pulled down with the code.
Are the libraries in the code?
Their libraries are in the PIO folder. So when I looked at it, git ignore had any .pio folder being ignored. So I took that out so that it got pushed up. I confirmed I had to push it manually up to Git to get it in there. But when I pulled it down to the Raspberry Pi, I'm still not seeing. I'm seeing the PIO folder, but it's pretty much empty. But it isn't on GitHub.
Oh.
Can you share some screens?
Pardon me? I don't have it right now. It's
not fit up.
Yeah.
Typically, if there's a git ignore and whatever you're doing there, I'm not. Which library? What language you running again?
That was Arduino. It was Arduino, basically in STM32s.
Now the language won't make any difference on Git,
Yeah.
but the one thing that I'm thinking is what you might want to do is start yourself out on just an entirely neutral platform, just like a desktop computer or whatever. Start into a new directory and do a Git clone of the whole project and just see what you get.
That's what I was doing. So I wipe it out completely.
When there's something in a git ignore like that, the intent is for that not to be ever in the Git repository, and that's a library you need to install from somewhere else to like an. Well, I mean, I'm accustomed with Node, so npm install, or if you're a Python world, you're doing a pip install, that sort of stuff. There's some other command you need to run to get that stuff in there.
I understand with Python or something like that. But with Arduino, basically, if I'm pulling the whole project down, I would think that the libraries that I've installed into that folder would come down with it. And like I
Pat,
say,
are those libraries already compiled, or are they source code?
those are source code.
Well, you know what you should do is just remove the git ignore file entirely from the project initially. Just don't have one and see what you get, because
Yeah,
it sounds like it might be related to that.
Hey, Pat.
Yep.
Pat, if you go to your project and you look in the library directory, are your libraries in that directory? Because in Platform.io, if a library, there's two ways to get a library. What's supposed to be in your, if you do it by their methods, what's supposed to be in the library directory is only libraries that you either create yourself or can't be sourced from the Platform.io default. So like if you, let's say you wanted to put the new ping library in your project. Well, if you go on Platform.io and you look up, you can look and download into your project the new ping library. But if you go to your library directory, it's not in there. So how did you add your directories? Did you actually literally put them in the library directory, or did you let Platform.io handle it?
So I let Platform.io handle it. I'm going to share my screen.
Okay.
So I do have it open here that I can go to. Pick my screen, share. And let's go to this guy. Can everybody see that?
Okay, now go to the library directory.
So if I go to my library directory is empty.
Right. That's because
wait a second.
That's
where
what
is this on your laptop or your target?
This is in my laptop. So this one I haven't uploaded yet.
Okay.
But when I go into my PIO folder and I go to libdepends, there are the three libraries I've added into my project.
Are they really there? Open up PID.
Definitely, they're there.
Yeah, okay, they're there.
And then you get ignore.
Yeah. So if I go to PID, so there they are.
Yep.
So they're definitely there. In my git ignore, so this right now it has PIO by default. I had removed it and then I had pushed everything up. And when I went into my GitHub, it was actually there.
Mm-hmm. So after you removed it, did you make a commit to add the files that it was ignoring before?
Yeah. So I made a commit. Everything was in GitHub. Okay. But when I went to pull it into the Raspberry Pi, it wasn't bringing, it would bring the PIO folder and it would bring the build and the lib depends file, but nothing inside of it. So when I go look, this one's for the Uno. So none of this was in there.
So did you bring it down to the Pi by a cloning fresh or by like a pull?
I did it with a cloning fresh. So that's why I was curious what was, if anyone's had any experience with this, what's going on.
That sounds...
So basically I had to re-download the libraries on the Pi.
Were you looking at the right branch? I mean, could it be something that simple?
No, there's only one main branch.
One branch.
So
that sounds like quite a puzzle you got, Pat.
It was something I was trying today. And I just wondered if anyone had come across that.
Nope.
And basically, because I'd assumed, hey, I'm developing on the Pi for the Arduino, so it should just pull all the libraries that were in there across. And it wasn't doing it.
I assume GitHub has a forum. This sounds like a forum question.
Yeah, possibly. So I just basically, I pulled it in manually, and I took care of the problem anyway today when I smoked the controller. So my little STM32, I had what is it, the ST-Link V2 little probe that plugs in a USB. I accidentally plugged it in the 4 pins backwards.
Ugh.
So yeah. which is interesting because now the USB port will not work at all on it, but I can still program the STM32 with the V-Link.
Serial port with the serial port.
Yeah. Yeah, but I can't access any of the data on it. I did release the magic smoke out of it.
It's amazing what that smoke can do.
I got to find a can of it and recharge it.
You know, Pat, that USB pass through that V-Link does.
Yeah.
It's basically reading the UART2, transmit and receive from the UART2, and there are pins for the UART2 separately available on the card. So there's a jumper. I can't remember, up on the front of right up next to the USB that disconnects that. So you can use that serial port directly. Depending on what you're talking to, that's TTL. So you'd need a max 232 or some kind of level shifter.
On the STM32 blue pill that I'm using, the little tiny blue pill boards, I think I'd have to find the traces and cut them.
Probably more trouble than it's worth.
Yeah. So if I'm unsoldering it, I'll replace it with a different board.
They're cheap.
Yeah. They're cheap. Delivery isn't.
You and Murray.
Oh, I know. Canada and New Zealand. We're taking it big time.
Murray will tell us about buying a $12 part and paying $120 to get it shipped.
$125.
So when I used to live in Sault Ste. Marie, Ontario, it was shipped to Sioux, Michigan to a drop box. And there's a furniture store we used to ship everything to. And then, hey, Friday after work or whatever, you make a trip across, pick up some milk, turkey, fill up the truck with gas, and pick up your parts and come back. It was free shipping.
Well, I feel guilty now about complaining that I can't drop by Tanner's anymore.
You guys were lucky to have a Tanner's.
Oh, you have no idea.
Yeah, for sure.
I live in a town of 5,000 people. We have a home hardware lumber store and a Canadian Tire store. And
that's all of New Zealand. That's all we've got in the whole country.
So
because we all know you don't have any Kentucky Fried Chicken down there. You'll get arrested.
No, we do have Kentucky Fried Chicken.
We do have Kentucky Fried Chicken.
Didn't somebody just get arrested?
You can go, you can't get KFC.
But somebody just got arrested for it, right? For a truckload.
I never heard that one.
Driving over the pandemic border and in and out of Auckland, yes.
Smuggling KFC.
Yeah.
They're hardened criminals, baby.
The guy with a lot of tattoos did that, by the way.
Yeah, you New Zealanders don't play, man. That's you guys are hardcore. That's all there is to it.
So Murray, how much would it cost? This is like a little padded envelope. How much would it cost to mail that from the U.S. to New Zealand?
Well, it's your postage. I mean, I put it this way. When I lived in Palo Alto, I went to a local ceramics show in the grass around Stanford, and I bought a bowl, which I still have. And I contacted the woman who made the bowl about a month ago, and she was happy to hear from me that I still had her bowl. And I said, "Can you make me another one?" So we have two. And so she's made me this bowl, lovely bowl. I haven't seen a photo, but I'm sure it's nice. And she went to send it USPS to New Zealand, and it ended up costing in US dollars $106 to send the bowl. And so she's going to send me the bowl and not charge me for the bowl. And I was like, wait, hold on a second, because she felt guilty of how much it cost to send that. But that package you have, John, would probably cost around $20 right now, just for a flat pack.
John, are you planning to send some things to Murray?
Yes, I am. Eventually, when we get our boards built here, sometimes after mid-December.
Yeah, our motor controller.
There's other
the same to
companies
Canada. That envelope would be about, depending where it was, $20 U.S. postal, or if it's expedited, with the courier service, $35 just for the little envelope.
Well, that's the problem. Is if it's U.S. Postal Service, it's as cheap as it's going to be. But if you go courier, like the FedEx, the smallest FedEx box that I can get is $125 U.S. So that's like 160 New Zealand, which is actually like 160 U.S. to you guys. So Think about a little box being sent for $160.
I send a couple boxes to my kids every year for Christmas and to Alberta, so within Canada. And it's anywhere from $100 to $150 to ship those 2 boxes.
Andy, were you about to say you knew of a cheaper alternative?
Well, I know when we were shipping back and forth like China and stuff, and I can't remember what's the yellow company, the DL something?
DHL?
DHL.
DHL, yeah. They were a lot of times who we used, but I don't know if they're going to be for overseas and stuff. They might be cheaper. I'm not sure.
They are cheaper than FedEx. FedEx is by far the most expensive. The problem I've had is that in New Zealand, a lot of the vendors in the U.S. only ship either FedEx or UPS, and those are really expensive. You can go DHL. That's actually is cheaper, yeah.
I'm not sure how they compare to USPS though.
What's the range on a carrier pigeon, or maybe an unladen swallow?
Perhaps two swallows could carry a board between them.
So who's going to make the solar powered surfboard that just drives over to New Zealand and delivers it?
A solar powered drone that could fly ahead of the light.
There you go. I think you'd be safer with a surfboard though.
That reminds me. Have you ever heard of IP over avian carrier? Somebody actually submitted an RFC for IP over avian carrier, and they did a comparison of how long it took to deliver a flash drive attached to a carrier pigeon versus the same amount of data over the internet. And it was in some country where they had poor internet, and the pigeon won.
hey, do not ever underestimate a 4-door wood-sided station wagon full of hard drives driving cross country and bandwidth, baby. I'm just saying.
Harold, I always heard that as 9-track tapes. Never underestimate the bandwidth of a station wagon full of 9-track tapes.
Yeah, but you need to look that up. Look up. It's an actual RFC that somebody submitted as an April Fool's joke, I think. It's IP over avian carrier. It's a real hoot to read.
Sounds like the kind that could actually get awarded.
Yeah, I'm probably going to be the last one in the group.
The other side of that is that we used to have a number of hams in the club. I don't know that we still do, but hams are okay. I don't want to insult you. Carl. Hams are of this. They're pickers and hackers. Their whole world is built out of junk that they got out of the dumpster behind the Radio Shack, and so this idea of having to order parts from faraway places is totally foreign. What you're supposed to do is look around and see what you got. What can I make out of what I got? I will say, just for my own ego, that Paul used the term hobby robots to differentiate from professional robots. I have always thought that what we did was better termed experimental robotics. And see, the difference is, it's like the difference between homemade and handmade, right? Homemade means not as good as you can buy in the store, but handmade means better. The space shuttle was handmade, right? Italian suits are handmade. So I believe we make handmade robots, experimental robots, and therefore we can lead the way.
So that's handmade experimental robots. That's 2 legs up.
Oh, we could probably keep adding on.
We're going to add an H to the DPRG somewhere.
Could be artistic handmade robots, because no 2 are the same.
Yeah, that's true.
We follow the artistic paradigm, which is just, poke around, see what comes out.
David, your robots work so well that I think your complaint is justified. And I was really referring to the kinds of robots that I build at home.
Paul, flattery will get you everywhere.
but your robots certainly work a lot more reliably than most of what we built professionally.
That's the highest compliment I've ever had.
But on the other hand, we were making trucks drive, and that was really fun.
So, Paul, your diagnostics that you showed us today that you're working on, is that part of a larger build that you're doing?
No, it was something that I did quite a few years ago, and I'm resuscitating my Ross stuff because I left my robot lawnmower sort of on the floor, as a stopped project back in 2013 when I went professional, and so I'm starting to resuscitate the bits of code that I had laying around there, and think about how to recast it into modern hardware and modern software. So it's all just a part of getting all that stuff back going again.
Well, we're real glad to have you back, Paul.
Thank you, David. I'm glad to be back, and I have to say the technical level in the DPRG has gone up a lot since I was last active in 2013. It's wonderful. It's impressive and great to see.
Wow, cool.
That's also encouraging. Wow, listen to us. Thanks.
Paul, I had a question for you. How do you your trucks that your big trucks that you're driving autonomously across the country, or is it autonomously or is it radio control or remotely operated? And then the other question is, how do you stay on the snow-covered highway?
So first, that we don't drive in snow, and we don't drive cross country. So
all of Canada is off your list.
I think if you come to the December talk, I'll talk about what the operational modes were that we supported and how they worked.
Okay, I don't want to steal your thunder from the show.
So I guess Canada is SOL, huh? In the winter.
Oh yeah. Only deliver things in the summer.
But 20 years from now, that won't be the case. So
exactly.
Yeah, that's true.
Yay, global warming.
Greenland is going to be green.
So everything south of the border will be baked, and we'll have lush Greenland here.
Pat, do you have snow right now?
Drive cars.
Have any of you seen Finch? Finch on Apple TV?
Not yet.
It's basically Tom Hanks builds a robot, and they go kind of across country basically, and there's adventures at Sioux. But what the problem is, there's been an ozone depletion. So basically, what he was just saying, everything around here is baked, and and they're trying to go someplace else because of stuff. And,
this is like Rain Man with a robot.
What now?
This is like the movie Rain Man, but with a robot.
No, not. No,
the buddy movie.
Yeah, it's a decent flick. I personally don't like how it ends, but because I think it just stops. I don't think we have a complete story, but maybe we do, and maybe I'm expecting too much. I don't know.
You don't like it how the way it ends because the robot dies?
I'm not going to say who dies or who doesn't die. I'm just saying it's kind of like as much as like Kevin Costner in Waterworld. I liked almost all of that movie, even though it went too long and all that kind of crazy stuff. But my biggest complaint is that it just kind of ended. We didn't have a completion to the story. It just kind of, it's like they ran out of money, which they did, and just stopped. so this is that kind of movie for me.
No closure.
What now?
Harold, Waterworld would have been 6 hours if they hadn't run out of money.
Well, I understand that, but and I agree with all that stuff. But I like just watching the whole thing and doing the whole stuff. It's just how that movie just kind of just stopped, and I'm like, okay, what next? And like the credits rolled, and I'm like, oh no.
So we need to give it an ending.
Yeah, we could give it an ending. And as he's sailing away, riding on his little hobby cat, a giant mega sharky comes up and eats him, and he all dies. Okay.
The end.
We know an Indian, or was it the mega piranha that got him? I'm not quite sure now.
Pat, is it snowing up there where you are?
No, they're threatening snow Thursday, Friday. So I woke up this morning. There was about 80 flakes on the back of the truck. So it must have had a little tiny dusting overnight, but no, there's still, my grass is still growing actually. It's hovering around today, let's say it was 38 to 39 degrees. So 3 degrees Fahrenheit or Celsius.
Strangely, we're heading into summer right now, and last night we had hail.
That's
So
because
last night, about 50 kilometers south of here, they had hail, freezing rain and hail.
well, I had seen a part of a women's soccer game being played somewhere up in Canada. I noticed that they had to shovel all the snow off the field. That's why.
Southern Ontario, like
Is that
400
right?
kilometers south of here, they got snow already.
Well, I'm going to sign out.
Hey, Dave. And
Carl, are we done?
I'm not detecting anyone else wanting to jump in. So seems to me going twice, going 3 times. Catch you all next week. Have a great night. Build robot. Bring presentations. Play harmonicas. Okay.
Roll call.
This is just going nowhere. Good night, guys.